Coming up next is Ritchie Vink. He's the creator of Polars and he's from the Netherlands. Let's give him a round of applause.
Yes, can you hear me? Some cool music as an intro. I didn't have such a cool intro yet. Hi, welcome. Thanks for being here. I'm going to talk today about Polars. Polars is a DataFrame library, and I want to have a quick show of hand. Who are developers here? Right. Who are Python developers? Right. Okay, cool. Who knows pandas? Who knows Polars? Oh, it's getting good. Great. Okay, then I'm glad that there is so much interest in the audience. Today, I'm going to first introduce myself. My name is Ritchie Vink. I'm the author of Polars. I have a background in machine learning and software development, and I also recently started a company around Polars, which the very original name Polars. Yeah. Today I'm going to talk a bit about Polars, but I didn't update my agenda, so it isn't entirely correct. This will be part of the topics, but not all of the topics. So it will be a sort of a surprise. So Polars is actually sort of a synergy between DataFrame libraries, which we already know and love, maybe, like Pandas, dplyr, and Datatable, and SQL engines. Because DataFrame libraries were usable in process, in memory, and gave you direct returns, and were very ergonomic to use, or very, yeah, you could use them in your favorite language, and you could compose them, and you could use them in your own functions, etc. If we look at database engines, we have to work with SQL. You have to go to another language. It doesn't feel as natural as using it from the scripting language you know and love. And if you write a query, it also goes to a database first, over the server, or at least to another process, which does its magic and gives you back the result. And in Polars, we want to have the best of two worlds. We want to have the composability and the data structures you have in DataFrame libraries, but we want to also have the good things from databases. And the most important good thing is query optimization. Databases do a lot of smart things to make sure you, yeah, you get your results as fast as possible. So this is essentially what Polars is. Polars is a query engine with a DataFrame front end. It respects decades of research in relational databases, and it comes therefore with lazy evaluation and query optimization. And query optimization just means we take your query and we're going to optimize it, and then we're going to run it. And this will can give you speed ups up to 10x or even more, depending on the query. Because if you run a query naively, it probably isn't the best way to get the data or the result we want. But we also take a lot of effort to be high performant, and we do this by minimalizing materializations. This means copy and write, or making operations slice aware. For instance, if I do a join, but I only need to take the first 100 rows after this join, we don't want to materialize this whole join first and then do the slice. No, we make our operations slice aware. We have data types which are constructed to amortize access and allocation cost. It's a bit technical, but for instance, if you allocate strings, you don't want to do a heap allocation every time you allocate a new string. This would be very slow and would also be very cache inefficient. Every time you would access that string, you would have a cache miss, which would be super slow. It's written in a low-level language to have full control over performance, over memory, over threading, and critical paths, and all the things you want to control if you want to write something performant. It's designed for effective parallelism. I want to underscore the effective here. Pickling something and sending it over to another process in Python isn't effective. It is parallelism, but it isn't effective. It's designed for out-of-core processing, so that means we can process data sets that are larger than your RAM size. And we have tight integration with I/O. That means we directly read into the memory in our own memory buffers, and we don't have to copy for another time by using another I/O library. And one of the most important things of Polars is the API. And I want to talk a bit about what we think is important for the API. And there was someone forced me on an issue to explain what I found important, so I called that the Zen of Polars, with a wink to the Zen of Python. And these are the things we think are important. We want to be very readable. We think readability and explicitness is more important than saving some keystrokes. We aim for a single return type per expression. The API should nudge to fast code. It should be pretty hard to write slow code, so you will not shoot yourself in the foot. We want to be pure in a functional way, so functions cannot have side effects. Underscore over concatenated words, and we want to minimize ambiguity. Someone said that some of these reasons didn't feel Pythonic, and I want to counter that there is no Pythonic way of writing things. Every Python standard library has different names. If we look here, some have underscores, others are concatenated. There's nothing to follow here. And one of the most important features of the Polars API are the expressions. The expressions are first-class citizens, and the type of expressions are sort of like this. They're a function who take in some state, and the state can be a data frame, another series, and some group by state, and they produce another series. And this function is composable. They don't take any other state than this, and they don't have any side effects. And because of this composability, you can do, it explodes. The amount of things you can do by composing different expressions is, it's super large, and it's hard to quantify what you can do with it. The state of the series can mean different things. It can mean a column, it can mean a group when you're doing a group by operation. It can be a list element when you're iterating over lists. It can be a single value, it can be a literal. So these are sort of the cornerstone of our API. And we are very serious about it. We are so serious that if we see that you're using a Python lambda, a custom function with some code, we're going to analyze this function and give you a warning when it could have been an expression, because this would have been really slow because you do something in Python. Here we're taking a string and loading that string with a JSON loads library from Python, and we smack you with a warning and say, don't do it like this, use the JSON extract expression. Credits to Alexander Beatty, he's over there. He helped a lot, did all the bytecode analyzing. And by following this warning, you can get I think you can get a 100x speed up, because you go from materializing Python strings, getting into Python strings, you keep everything into the Polars engine. And with our API, we want to make the following promise. If you use our API idiomatically, you will get one, C speed, factorization, similar to NumPy. You get optimizations. We will analyze the expressions and we will optimize it. For instance, if there is you do a sort and then a head or a slice, we can swap this sort expression with the top K expression, which is algorithmically much cheaper to do. You get parallelism. We do a lot of parallelism in Polars, and we do this effectively and implicitly for you. You don't have to think about it. You just write your queries idiomatically. and you will get out-of-core analysis. So you can process data sets that are larger than RAM. So I want to go to a few of those. The first one is optimization. And I think this is a little bit different from what we are used to in NumPy. In NumPy, we are used to getting C performance, but NumPy is still eager. So if I write my NumPy query or my NumPy script, every operation is executed immediately, and NumPy will not take a look at the whole expression as a whole and say, hey, this buffer can be reused, or hey, you're multiplying this column times 1, this multiplication isn't needed. It just does this multiplication, even though it's redundant. So we are a bit more lazy. We take an expression and we're going to analyze this expression first, and we're going to do optimizations like constant folding, replacing operations, changing algorithms, yeah, a lot of optimization. So you get two things you can get with a compiler. You get the C performance, and you get just-in-time it's not just-in-time, but you get some optimizations as well. And this can give you a huge speed up. So here we have a query written. We load some data from a Parquet file, we do a filter, we do a group by, and then we do 2 aggregations. And first we run this query without optimizations. We explicitly turn them off, which takes a little more than a second, and then we just run the same query with optimizations, which takes only 230 milliseconds. So we get a 4.5 speed up by just for nothing. The optimizer just optimizes this query and gives you the speed up, and you didn't have to think about it. One of those optimizations you get, for instance, is called common sub-expression elimination. Here we see 2 aggregations. Or we see that we multiply 2 columns and then we do an aggregation. One is a mean aggregation and one is a sum aggregation, but this multiplication is done twice before we do the aggregation. So you can just write this query, and under the hood we will translate it. We will create a temporary column first, and then we do the aggregation. There are a lot of optimizations we do, and I can give a whole talk of going through those optimizations and explain why they benefit or why not. Here are a list of a few of those. We do schema checks, and this is a really important one. Before we run the query, we check the schema, and we check if the data types fit. So, for instance, you cannot multiply, let's say, you cannot do a string operations on a floating point number. So if you have written this, you will get an error. But the point is, you get this error immediately when you run the query. You don't get this error 20 minutes later when the query is finally at the point where you do this operation that is not allowed. No, you get this error immediately. And this is very important because the iteration time when you're doing engineering, ETL engineering, is important. It's very frustrating to be a day in a query and get this error. We do projection pushdown, which means we select columns as early as possible. So if you end with a select, we will try to push this select all the way to the file readers. And when we read a file, we don't read those columns. We don't read those columns from CSV. We don't have to parse those columns. We don't read those columns from Parquet. In Parquet, we can actually just skip those columns up front. We can see where the columns are in memory or on disk, and we can only read those columns. We do the same for predicates. Predicate is a fancy name for a filter. So we also push filters down to the file level. And in Parquet, there are even statistics in the file, and we can use those statistics to determine if we need to read this file or not. Otherwise, we will just read the file and we will apply the predicate as soon as possible, so the memory pressure remains low. We do joint branch reordering, so we try to determine up front which branch we should evaluate so we can keep the hash tables lower, smaller, and have less memory pressure. We do scan sharing, so files that are read multiple times in the same query. For instance, you do a self-join, or you have something that's recursive in the same query. We share the scans. We cache them, or we share them in the same operators. We do commoner subplan eliminations, where we prune queries from the same source. You saw the one with the common sub-expression elimination, where we see two expressions are similar and cache an intermediate one. And we make sure that types are coerced and allowed. And the second thing you get is parallelism. And the method we use for this is called work stealing. And we are publishing tasks. So every expression can be subdivided in different tasks and they are published to a queue. So let's say I have a thread pool of 3 queues, where every queue points to a core on your machine. And that core will get work from that queue. We can publish work to the queue, and the queue will do the parallelism. The publishing task is super cheap. We don't need to serialize anything. We don't need to do anything via pickle. We just put a pointer of the task or a function of the task on the queue, and the thread will start processing its queue. When a thread has finished publishing its queue, you can see that in the second image. It's done. It has cleared its queue. It's got no work to do anymore. It will steal the work from another queue. So it just takes the task from another queue, divides it in half, and say, hey, I can process these for you. There's a slide overhead on stealing, work stealing, because we have to use mutexes, but we're talking about, we're still counting nanoseconds here. And there is no contention between threads. The OS doesn't need to swap between threads because we don't use more threads than our thread pool. If a task is not ready to be executed, we don't start a new thread for the task. No, we put it on the queue and it will eventually start running. And this will make sure that we are very good at saturating the threads on your machine. It's very common in Polars that if you look at Polars doing its work, that all your threads are fully utilized and they keep fully utilized because they share the work. And the only thing we have to do on Polar side is to make sure that the threads are equally sized or small enough so there can be work stealing. If there is one task which would be super large and the other ones are super cheap, then that single thread will keep working on its long task. But this is something the user doesn't have to worry about. This is how we do it, and we try to make sure that this works implicitly for you. Here's an example of how we do work stealing. Here we create a data frame with some integers, and we make sure that they're groupable by doing a modulo of 1 million. So we get 1 million groups. And the first one we run in the .select, which is on the whole column. We take column A, B, and we compute the number of unique elements. And the number of unique elements requires a group by internally. We need to create some hash tables, and we need to compute the number of unique elements. And implicitly on the hood, we will create multiple tasks for every group. We will divide this work in multiple tasks. It's n unique. For the ×2, we don't, because a multiplication is often super cheap. And we don't want to do extra parallelism here, because it would be cheaper to just do the ×2 than to create new tasks. So this is how we would create a parallelism scheme for the select context. If you do a group by and then an aggregation, in that case, we would parallelize over groups. And because we already have a lot of groups, potentially have a lot of groups, in this case you have 1 million groups, we don't split the n-unique again into multiple tasks. We do this per group. So the group by aggregation and the n-unique is all done on a single task. And again, the ×2 can be done without parallelism, because we can just ignore the group state, because everything needs to be multiplied ×2. So it would be more expensive to keep track of the groups when we do this ×2 multiplication, and just ignore the groups for now and do the ×2. So this is something you don't have to worry about as a Polars users, but it shows that it gives you an idea of how Polars manages the parallelism for you. This work ceiling works via thread pool. This thread pool is global. This means it's not bound to a single query. And that means you can dispatch work on Polars in work schedulers like Airflow. You can just say fire this query and give me the result, and you can do this concurrently or in parallel, and you will not smother the system, because the thread pool is shared, and the parallelism the task will be spread between the different queries. So this makes it very easy to use Polars behind a work scheduler, or behind multiple threads, or behind a server. For instance, if you would have a server which would be threaded and would start a query without a work stealing mechanism, then you would have many threads doing compute, which would cost a lot of OS swaps of the threads. Would take a lot of, it would be expensive. So yeah. And the third thing you get is performance, because it's written completely from scratch in a low-level language with C and C++ performance. This is the ROS language. It allows us to control every performance-critical code branch. It allows us to write cache-efficient code. We use explicit SIMD and auto-vectorization. SIMD is a parallelism mechanism on the CPU where a single thread can work on multiple integers or multiple floats at a single swap, or at a single clock tick of your CPU. We reuse memory buffers, and as we said, we parallelize effectively. So this is the same promise you get with NumPy, but different from NumPy, we also support nested types. We also support string types. We support more types to do this on a C-like performance. And as a result, Polars is very fast. Here are some queries from the TPCH benchmark. Here we see different tools that are in the same space, in the data processing space. Yeah, we have good performance. We have good performance due to parallelism, due to our algorithms, due to where we have written Polars. You can see more on the website. And with that, I want to thank you, and I want to invite you to go to the GitHub page, give us a like, and go to our Discord. Our Discord is super active. There's a lot of help. If you want to get started, the Discord is definitely the place to say hi. And there's a lot of very short notice interactions. There's a great community there. Yeah. Thank you. Are there any questions? Yes. I think you need to get a mic.
Hi.
Oh, yeah.
Okay. Okay. So I just wanted to know, is Polar can be used in conjunction with PySpark? So is it a good option to use both together?
You can, well, in PySpark, you don't want to materialize to a single node, I think. Polars is single node. But if you do, what we see people using is is going vertical scaling instead of horizontal scaling. There are a lot of users of Polars who say, hey, I ditched PySpark and we just went for vertical scaling and go to a 1 terabyte machine, for instance, and say, well, the setup was much simpler and we get a lot of parallelism and it's also faster because you don't pay for the I/O to go to the different servers on a single cluster. So combining them, it's possible. There is a Fugue project which allows you to run Polars queries on a PySpark cluster and does the mapping and the reducing for you. That project is called Fugue. Take a look at there. And if you're processing maybe 500 gigabytes, maybe think of considering vertical scaling instead of a cluster. Yep. Any questions?
If I can interject, I'm going to ask one of my own. Do you support GPUs similar to Rapids does and Wrapping Pandas, or do you plan to do that?
I think the question was if we use GPUs similar to another...
Rapids.
Ah, yes. No, we don't. That would be a huge effort. And I'm also not convinced it's the way forward for us because the CPU is quite limited to memory and CPUs are very, or GPUs, sorry, are very expensive and moving data in and out of that memory is also expensive. So I think you will be a lot of times memory bound. I think for the simplicity of being able to scale more, the CPU is our workload, is our goal. But maybe NVIDIA will take this on in the future. That would be cool. Yeah. Yeah? Okay, thanks. That was it, right?
And also with questions?
I have a question. So, how easy is it to take Polars and then put it on a cluster? If you want to have the solution that you're working on, if you want to have that running in a cluster, how would you do that?
And by the cluster you mean multiple machines?
Yes, multiple machines.
And why would I would say, so Polars is made for single node, but single nodes can scale to terabytes at the moment. So the goal, and Polars can do out-of-core processing, so you can process data sets that even don't fit into RAM. So we are focusing mostly on the rethinking, do I need a cluster and can I do it on a single machine? Because you have less I/O overhead. If you can scale the machine down, it can be a lot cheaper. We're not focusing on the cluster question at the moment.
Okay, because that would be really interesting because you have all these nice optimizations in your code. If you could tell Polars, I'm running on a cluster, and then say instead of using threads, you also use cluster nodes, then you could use the same optimizations for then running your code on a cluster, and then maybe on each node have threads running as well. So to basically have a very nice optimization of your workload.
Right. So I think there are some optimizations which make sense in the general scheme, like predicate pushdown, projection pushdown. But if we look into the hardware, things that are cheap doing parallelism on a single machine are not, that same kind of parallelism isn't cheap on a cluster. If I need to send this to this function and the data to another cluster, then, so the assumptions we make for a single node are completely different from the assumptions you make from going over the wire, going over a network. And I think if we would go for a cluster, we would make a distributed plan on top of what we do in Polars and say, okay, this node is going to do this computation plan, and this node is going to do this computation plan. But it wouldn't use the parallelism we do at the moment translated as a clustered parallelism, because those assumptions don't hold. the latency is completely different. Yeah.
Okay, that's certainly true, yes.
Yeah.
Thank you.
Yep. Okay, thanks.